Electronegativity is symbolized by the Greek letter chi, so it looks something like a fancy X. Electronegativity is the attraction an atom has for a shared pair of electrons. Now, if you think about those words, shared pair, it implies that the electrons are involved in a bond, because that's where we think of sharing electrons. This electronegativity scale was developed by Linus Pauling in the 1920s. The scale doesn't have any units, and his scale came from looking at ionization energies and something else called electron affinity, which we don't study here. By putting these two together and trying, in a sense, to come up with a measurement of the attraction that the atom has, or that the nucleus has, for a pair of electrons. One of the things that you might notice is that there are no values for the noble gases in the original Linus Pauling scale. When he came up with the scale, at the time, the noble gases were not engaged in making any covalent bonds. Now we know that some noble gases under certain conditions can indeed engage in covalent bonds, and other scales actually give electronegativity values for the noble gases. The scale that is in front of you is the most common, and we will use it in this course. I find it a little bit remarkable that right now we're introducing the electronegativity scale as part of the periodic trends. But one of the things is you're going to see this scale over and over again, and you're going to be using the concept of electronegativity over and over again, especially if you carry on to other courses in chemistry. Now, of course, you don't need to know any of the exact numbers, but you need to be able to understand and explain the trends. So first of all, let's state what the trends are. So of course, across the periodic table, I think you can see that the numbers get larger. In the Linus Pauling scale, fluorine has the largest electronegativity. And you can see that the lowest electronegativities occur for the metals. They have the least attraction for the shared pair of electrons. Electronegativity goes up across the periodic table and goes down the periodic table. In addition to being able to predict the trends, I think it's also important to look at those elements, nitrogen, oxygen, fluorine, chlorine, and realize that they have really high electronegativity values. These are the most electronegative elements in the periodic table. And kind of keeping that in mind will help you explain a number of things, especially when we get to looking at polar bonds. Let's look at developing an explanation. Again, I'm scaffolding this for you. If you're asked to explain the trend, this is the sort of explanation I'd like you to make. Across the periodic table, the first thing we look at is the nuclear charge. And of course, the nuclear charge indeed increases across the periodic table. This results in an increase in the force of attraction between the valence electrons and the nucleus. And then, of course, this also results in an increase in electronegativity. Because, of course, electronegativity is directly related to the force of attraction between the valence electrons and the nucleus. The valence electrons, of course, in this case, are being the shared pair of electrons. Now, down the periodic table, the distance between the valence electrons increases, and therefore, of course, the force of attraction goes down. And, of course, the electronegativity will go down because, again, the force of attraction for that shared pair will go down. Now, let's apply our knowledge to make a prediction about the trend in electronegativity. So in the next key question, you'll see that you're asked to arrange the following according to increasing electronegativity. This is very similar to the question that we saw concerning atomic radius. In fact, it's the same element. So of course, to do this exercise, you'll need to refer to the periodic table. I ask you to stop and make the prediction yourself. Okay, so the approach here should be to look for the element that has either the greatest electronegativity or the smallest electronegativity. The one with the greatest electronegativity, of course, will be that element that's towards the right in the upper part of the periodic table. And so, of course, that'll be oxygen. That's the one with the greatest electronegativity. The elements with the smallest electronegativity will be found further down the periodic table and towards the left. And of course, that will be barium. Because we're asked to rank according to increasing electronegativity, we'll start with the barium. So we've got barium, and then moving up the periodic table and to the right slightly, we come to scandium. Moving across the periodic table, we come to gallium. Moving up and then to the right slightly, we have carbon, and then finally oxygen. We need to apply our greater than symbols And in this case, of course, it's oxygen with the greatest electronegativity and barium with the smallest. So once again, we've looked how to state a trend, we've looked at how to explain a trend, and we've applied our knowledge to making a prediction of an arrangement of elements according to the trend. One further comment concerning doing explanations in relation to periodic trends. You should always start your explanation with the core principle. The core principle across the periodic table is that the nuclear charge is increasing. The core principle down the periodic table is that the valence electrons are found further from the nucleus. Sometimes students will try to use one periodic trend to explain another. So for instance, a student might say, across the periodic table, the atomic radius is getting smaller, therefore the electronegativity is increasing. This is not an appropriate explanation. Again, you should start with the core principle. Across the periodic table, the nuclear charge increases. Therefore, the force of attraction between the valence electrons and the nucleus increases. Therefore, the electronegativity gets larger. And therefore, the atomic radius also gets smaller. Using the core principle is where you should start. The next trend that we will explore relates to the ionic radius. Because this trend is a little more complicated than other trends, we will discuss this in our live sessions.